Howdy, PreCal. It is Miss Kosh, and today we are going to cover 3B, which is graphing logarithmic functions, and then a little bit of review of what we did with exponents. So as we get started, a logarithm is the inverse of an exponential function. And so we can convert from exponential to logarithmic form and back. We can go back and forth between logarithmic form and exponential form. And one way that we like to do that is we joke about, we have the I heart logs. So do you see how it kind of, sort of makes a heart? To go to exponential form, this becomes a to the y equals x. So we do the I heart log. So do you see that? We followed that process there. And sure enough, this was a to the y equals x. When we go from exponential form to get to logarithmic form, I put form and log together and said fog. Oh, my apologies. This is the base in our exponent, and the base in a log is down here. And so when I go to find the logarithmic form, I often will double check because I find it easier to go from log to exponent than exponent to log. So a to the y equals x helps me double check, and that's the logarithmic form. Okay, if they don't, so here's the base on this one. Our base is 3. Our argument is that 81, and 4 is the answer. So to change this, we do 3 to the, so I heart logs, 3 to the 4th is equal to 81, which is a true statement. If the base is not written, and they use they have the notation log, something like this, then it's understood to be a base of 10. If you see what we call the natural log, I'm not seeing an example. The natural log would be something like ln of 4 or whatever. This has an understood base of e, and e is about 2.71. I forget all the decimals. It behaves similarly to pi. It's an irrational number. And so anytime we see ln, that means it's got an implied base of e, so you would just write natural log of 4. We don't typically write the e. A common log would be like log of 42 or something, log of 6, 7, all right, sorry. So something like that is how we would write that, but it has an understood base of 10 that we don't usually write. Okay, so convert from exponential to logs, logs to exponents, and exponents to logs. So this is I heart logs, so 10 squared equals 100. I heart logs, 2 to the 4th equals x minus 1. You can put parentheses here, but since nothing else was on that side of the equal sign, you don't have to. I heart logs, 3 to the 4th equals x plus 6. Okay, then we'll go from exponential to logarithmic. So this one, our base is 2. So log base 2 of 16 equals 4. And then we can double check 2 to the 4th equals 16. That's what we had before. Whenever I see the e, I think natural log. So it's got an understood base of e. So natural log of 5 equals x. Let's double check. E to the x equals 5 was what they had given us. Here our base is 5. Log base 5 of 9 is equal to 2x minus 1. This base is a 3. Log base 3 of 18 equals x plus 2. Super. Okay, evaluate the expression. Okie dokie. So with this one, if we want to go solving this, we could set this equal to x and then convert to exponential form. So 4 to the x equals 64. Well, I might remember, I like to play the game 2048, so I would encourage you to play it because it starts getting these numbers in your head. I have 2, 4, 8, 16, 32, 64. I might remember that 64 is 4 cubed. I also might remember that this is 2 to the 1, this is 2 squared, this is 2 cubed, this is 2 to the 4th, this is 2 to the 5th, and this is 2 to the 6th. I know that this is 2 squared to the x, which would be equal to 2 to the 6th. Well, power to a power, this gives me 2 to the 2x is equal to 2 to the 6th. And now since the bases are the same, we can set the exponents equal. I divide by 2 and I get x equals 3. I might have also remembered that, that this was 4 to the x is equal to 4 to the 3rd, and therefore set the exponents equal. But maybe you forgot and you knew it was a power of 2. Great. Okay, on this one, set this equal to x. 6 to the x is equal to 1 over 36. I know that 36 is 6 squared. This is 1 over 6 squared. Well, I want this 6 to move from the denominator back to the numerator, and I can do that by making the exponent negative. Now the bases are the same, and so my answer is just x equals negative 2. All right, another I heart logs. 16 to the x equals 2. Well, I know there's a 2 and here's a power of 2. This is 2. I'm counting on my fingers, which you can't see. 2, 4, 8, 16. So this is 2 to the 4th to the x is equal to 2 to the 1. Power to a power, we multiply. This becomes 2 to the 4x equals 2 to the 1. 4x equals 1. Now I divide by 4, and I get x is equal to 1/4. Cool. Okay, this one set it equal to 0. This is actually a property. 2 to the 0. I knew the answer. I'm sorry. Let's set this equal to x. Sorry, I know that this property is going to equal 0. So I just jumped straight to the answer, but that wouldn't help you understand it. So 2 to the x is equal to 1. If I raise 2 to the 0, well, okay, 1 would be like 2 to the 0 power. And so x is equal to 0. Or in a second, we're going to talk about how that's a property. Log base anything of 1 is equal to 0. Okay, now look at this one. Check this out. So set this equal to x. If I go 5 to the x equals 0, you may remember this is like saying 5, if I raise this to a ridiculously large negative power, okay, this would be like 1 over 5 to that ridiculously, I'm not going to write out all those zeros, ridiculously large power. This is my example of you have $1 that you're sharing with the whole world. Okay, it's not 0, but it might as well be. So it starts approaching 0, gets ridiculously small, but it's not 0. So this has no solution. There is no exponent that you can raise 5 to get 0 as an answer. So not possible. Okay, so some logs are a little trickier to work with. So with this one, like if I set this equal to x, I have 3 to the x equals 8. If I do know that 3 squared equals 9, and I know that 3 to the first equals 3, so it's going to be some number between 1 and 2, but I don't know what it is without using a calculator. Back in the day, they would have tables, but we don't have to do that. So on your Casio, if you hit the math button that's kind of on your main screen, and then you under that math button, there's this log AB, and what it lets you do is it'll let you have like something here and something here. Which means that you could then change this, what was it, log base 3 of 8? So then you could do log base 3 of 8 like that in your calculator. And then I added this with Desmos. If you go to function, so if you hit that function button, under the calculus stuff, there's this log base A thing. And if you hit that, then it would let you say log, and it gives you a little something here, and then you can come up here, and we would do log base 3 of 8 there. We can also use the change of base property, but I'll teach that in a second. So, okay, so here are the laws of logarithms. We mentioned this one briefly. Anything, so keep in mind b to the 0 equals 1. Any base, as long as, we won't have a base that's negative or 0, or actually even 1, we wouldn't do that, but we can have any other number, and if you raise it to the 0 power, you get 1. Log base b of b is 1. So if you think I heart logs b to the 1 equals b to the 1. On this one, log base b of b to the x is just going to be equal to x, and that corresponds with b to the log base b of x also equals x. With these, when the bases match, you're just left with whatever that exponent is. Okay, continuing on. If I have an exponent here, oh, my pencil turned off. Okay, if I have an exponent here, I can bring it out front. And so log base b of x to the m is equal to m times log base b of x. If I'm multiplying two things together, notice we're taking the log of two things that are multiplied together. So there's just one log, but it can be split apart with two logs, and it becomes log base b of m, plus log base b of n. Subtraction and division go together. So with the division, log base b of m over n equals log base b of m minus log base b of n. And then this one has a name. It's called the change of base property. And this is how, a second ago, do you remember how we had this log base 3 of 8? You could use the change of base property and say, okay, well, this would be log of 8. So whatever's the top number goes to the top, and whatever's the bottom number goes to the bottom. And the base can be anything in the whole wide world as long as they match. So right now, I wrote it so that they're 10. You could do it so that it's natural log, so it's base of e. I could make it the log base 1, 2, 3, 4 of 8 over, I don't know why I would, but I could. As long as those bases match, all of these 1, 2, 3, 4 different things are all equivalent to each other. Do I have Desmos pulled up? I'll show you. Oh, there we go. I'm not sure what I was working. Where are we? Okay, so function, I have to go down a little bit to, where's calculus? There it is. So log base, okay, so I said log base 3 of, and then come over to 8. Oh, that's funny. Let's see what, nope, it doesn't like that. Let's come in and do 8 here. There we go. Okay, I said that it would work if I did, let's make that very, I'm too lazy to open up my keyboard and get the word log. Log base 8 over, I should just type in log, that would be so much easier. Log base 3. And sometimes it's easier for me to type that in. Notice that they're the exact same decimal approximation. I could also do, typing would be faster, natural log of 8 divided by, yeah, okay, natural log of, on my keyboard on my computer, it's much faster. So I might need to type, might need log base 3 of 8. I might need the decimal approximation. And for me, on my keyboard, it's faster to do natural log of 8 over the natural log of 3, and I get the same thing. So I can use that change of base property. Okay, go away. Now let's see, so we're going to expand these. So what they like to do is they like to have us go back and forth to expand them out or to condense them. So looking at this one, we have the property where I see some multiplication. So multiplication can be split apart with addition. And then I also see that I have this exponent that can come out front. And that's as expanded as we get. Okay, on this one, I see some division, which can be expanded with subtraction. And I now see an exponent that can come out front. Cool. Okay, this one, all we can do, this parentheses, it stays the same. It's done. It cannot change from its entirety. I can't distribute the natural log through. I have to take a number, subtract 3, then take its natural log. And it doesn't work where you distribute through. So this is all we can do is move that exponent out front. That's as good as it gets. Okay, is that the end of those? Okay, yes. Now let's condense. So this, I see addition, which can be condensed with multiplication. I would be okay with that answer. I would also be okay with when you actually FOIL it. I see an x squared. When you multiply x times x, I see a negative x, and a negative 2x is a negative 3x. And I see a positive 2, I FOILed, and they're all in that parentheses. And remember, this natural log has an understood base of e. I don't write it, but it's there. Okay, on this one, the first thing I would do is deal with that 2 out. Oh, well, goodbye. Come back. This 2 becomes an exponent. So it becomes log of x squared minus log of 6. Subtraction gets condensed with division, and it divides the numbers. It doesn't divide the logs. That's the change of base property. It's something different. Okay, so now I see log of 3 squared, which is 9, plus log of x cubed. So this becomes log of, they're being added, so they would multiply. So 9 log base 10 of 9x cubed. I wouldn't say log base 10 typically, but I wanted to remind you that we have an understood base of 10. Come back. I would say this is log 9x cubed. Okay, and so now when we graph them, our parent function, we're using a small base here because it lets us, it doesn't take as long to grow. Let me show you what I'm talking about for a second. If I come over here to my functions and come down to calculus and find this. Okay, so if I have log base 2 of x, and let's hit that little home button right there so we get a normal looking thing. Let's also look at the table. I'm going to plug in some powers of 2. So 4, 8, 16, 32. Okay, so now we can see it's growing, and they do grow But this is going to grow a little bit faster than if I just did, where did you go? Log of x. With that one, this now has an understood base of 10. Okay, if I find this one's table, I need powers of 10. So I have to plug in 10 to get to 1. I have to plug in 10 squared, which is 100, to get to 2. I don't get to 3 until 1,000. I could scroll out and find it, but I mean, it's just kind of, that's ridiculous. Let's go back to the home. So they have the same shape no matter what that base is, but the smaller the base is, the more realistic it is for us to plot points and graph them. Does that make sense? I hope so. Okay, so back to this problem. So what we have, this is the, we can look at our base of 2. I know if I plug in 1, I'm going to get 0, because we said log base 2 of 1 is equal to 0. If I plug in 2, log base 2 of 2 is 1. If I plug in 2 squared, that's 4, then I get log base 2 of 4 is equal to 2. So here are a handful of points. I have 1, 0. I have 2, 1. I have 4, 2. I have 8. I think this would be 8, 3. And then I'm going to start, as if I plug in, I can't plug in 0, so I have an asymptote here. And if I plugged in 1/2, I'd get, plugged in 1/2, I get -1. And so it starts looking something, let's see if I can hit the points a little bit better. So, it doesn't double back. Okay. Ish. I don't like the end of that. Anyway, something like that. Okay, so it grows, but it grows slowly. So it always passes through 1, 0, and then B, whatever the base is, 1. This is what I would call that pivot point. Remember how we talked about that in the other, in exponential functions? We have a vertical asymptote at x equals 0 unless we have some transformations that start shifting it around. Our domain goes from 0 to infinity with a soft bracket. You can't take the log of 0 or the log of something negative, so that's not possible. And our range goes from negative infinity to positive infinity. Our end behavior, we're not going to approach, so notice on this one, we're approaching positive infinity with our x, but we're not approaching negative infinity because we can't. All we can do is start approaching that asymptote at 0. And when we approach the asymptote doing something like this, we're going down to negative infinity. When I approach the infinity, I'm growing slowly, but I am growing to positive infinity. Oh, the pivot point, it's written there. Okay, fantastic. Okay, so you'll notice if these are exactly inverses. So this would be, if I have 2 to the x, there are my powers of 2. When I switch this around, I have, when I plug in, they're inverses. Think about this, log base 2 of 8. Another way to think about this is log base 2 of 2 cubed, which is 3. Okay. Let's keep going. I just like to put my name on every page. I claim my work. Okay, so list of transformations. This has a vertical stretch of 2. And it's going to go to the right 3 and up 5. Okay. Ooh, we've got all sorts of things happening here. There's a negative log out front. The negative log makes it go from this to like this because it flips it over that, anyway. Something like that. Does that make sense? So instead of increasing but slowly, it's going to be decreasing. Okay, go away. But I also need to take away this. I also need to consider this. Oh, nope. I need to factor out a -2. And when I do, I get a +2. And then, another parentheses. Oh, my goodness, -6. So this has been it's been reflected over the x. It's been reflected over the y. It's got a horizontal dilation by a factor of 1/2. And it's going to go to the left 2 and down 6. That has got a whole lot of stuff happening. So we started with a graph that looked like this. Then we reflected it to look like this. Then we reflected it over the y-axis. And so now it's doing something like this, sort of. So anyway, kind of complicated. We'll graph some. Okay, on this one, 1/3 natural log of 1/2 x plus, well, what's half of, I think we're going to have a 14 here. Half of 14 would give us 7. So this has got a vertical dilation by 1/3, a horizontal dilation by 2, and then it's gone left 14. Okay, I graphed some of these already to make the video a little shorter. We're kind of already we're not a short video already. Okay, I'm going to stop here and let you come back for the next video to see the actual graphing. So we'll have a part 2 in just a minute. All right, like, subscribe, comment, and go practice.